Hello, everyone, and thank you for joining us for today's webinar. This session is part of the Passive House and All Electric Homes Training and Workforce Development Initiative brought to you by the sponsors of MassSave. MassSave is a collaborative of Massachusetts electric and natural gas utilities and energy efficiency service providers, also known as the sponsors, helping residents, businesses, and communities of the Commonwealth save energy and money by improving the energy efficiency of our buildings. As part of this training initiative, the sponsors offer a 50% cost reimbursement for individuals pursuing professional accreditations for either Passive House or Energy Star. Once you have successfully completed your certification course, you can fill out the reimbursement application found on our website and submit it to us for incentive processing. The sponsors of MassSave also offer robust incentives to homeowners, builders, and developers who incorporate energy efficiency upgrades into their design and build high-performance all-electric homes. To qualify, single-family homes or buildings with 1 to 4 units must have heat pumps for space conditioning and electric appliances for water heating, cooking, and clothes drying. Homes can qualify for incentives through one of 3 eligible performance tiers, which include a base tier for homes that exceed the building code, as well as tiers for Energy Star, Next Gen, and Passive House certification. Incentives start at $7,500 a home and also feature innovative market transformation adders, which are designed to encourage participants to pursue additional national certifications for their homes and to incorporate emerging equipment technology to drive higher building performance and enhance occupant comfort. For multifamily buildings, the performance tiers and incentive structure is similar to that of single family, with the biggest difference being that multifamily buildings are allowed to have fossil fuel domestic hot water heating equipment while remaining eligible for incentives. Please note that the program defines low-rise buildings as having 3 stories or less, while high-rise buildings have 4 stories or more, or any multifamily building with centrally metered utilities for tenants. There are some slight differences in the per unit incentives for low-rise versus high-rise buildings, as you'll see in the chart on the screen. And lastly, there are some additional market transformation adders for multifamily buildings, including more options for heat pump water heating equipment, as well as incentives for whole building air infiltration testing. If you have any questions about these incentives, please do not hesitate to reach out to us at the email addresses shown on the slide. And with that, I will turn it over to we've got a great panel of folks here who worked on the Acton all-electric house, starting with Jordan Goldman of the ZeroEnergy design, Laura Burns from Adams and Beasley Associates, Dave Wittig from Adams and Beasley Associates, and Mike Browne from Advanced Building Analysis. So thank you all for joining us. Really excited to have you here today. And I will pass the mic off. Jordan, I believe you're first.
Great, thank you, and thanks everyone for joining. That one's not mine. That one's mine. Keegan, will you be forwarding the slides?
Yes, sir.
Okay, so as Keegan mentioned, I'm the engineering principal at ZeroEnergy Design. We are an architecture and engineering firm out of Boston. On this project, we were the architect, we were the HVAC engineer, we did design, energy modeling, and we were also the Passive House consultant. Can you go to the next slide, please? So this is a 1600 slab on grade 2-bedroom, 2-bath house designed for a single occupant. It is in Acton. Specific goals of the project were energy efficiency with the goal of Passive House certification, which this house did achieve. Healthy indoor environment. Overall simplicity. You'll notice the form of the building is very simple, which has got lots of benefits when you start to incorporate some of these energy efficiency techniques, and overall low maintenance. So simplicity and low maintenance often go hand in hand. And so the efficiency of the building starts with the building envelope. It's quite literally the foundation upon which the building is built. The efficiency is built. And so we utilize continuous insulation for the whole building and paid particular attention to the junctions, because that's often where your kind of thermal envelope breakdowns happen, if you will. So I mentioned this was a slab on grade. We used a monolithic slab as the foundation of this building. So it's got a thickened slab edge, and we used EPS insulation underneath the entire slab, which then wraps under your kind of thickened edge or your footing and turns up at the perimeter in order to meet your above grade wall continuous insulation. We like using products like EPS instead of XPS just for overall environmental friendliness. XPS happens to use a very bad blowing agent. So the result is that you are kind of actively contributing to climate change through the use of this material while you're ostensibly trying to save energy and help combat climate change. And so similarly, we were focused on other materials that we used. So we used cellulose as the cavity insulation for the wall and the roof. And we used wood fiberboard as our continuous insulation for the exterior walls. Cellulose and wood fiberboard are both kind of like plant-based. If you stretch the definition a little, wood fiber comes from kind of compressed and bound sawdust. So a waste material that's being kind of reclaimed and used as a rigid insulation material. And cellulose comes from recycled paper, cardboard, and newspaper. So you'll see on the detail on the left, the slab insulation wraps up at the perimeter to meet the above grade wall insulation. And the detail on the right shows our top of wall condition. We had an 18-inch deep roof truss filled with dense packed cellulose. And you see where they come together, very, very little thermal bridging to kind of maximize the overall effectiveness of the detail. Next slide, please. And I will pick it up. The detail on the left shows our eave end condition, and detail on the right shows the window. These are impossible to read, so I really won't focus too much other than to suggest that, we were very focused on maintaining insulation and air barrier continuity all throughout the house. So it started with your sub-slab continuous insulation. This is, styrofoam coffee cup type material, a little bit heavier density. Next slide, please. Which then gets covered with a continuous layer of 10 mil polyethylene. This serves as sub-slab vapor retarder and air barrier. All the seams were carefully taped. Any penetrations through the slab were carefully taped in order to maintain our air barrier continuity. And actually, can you go back one? And you'll see that, if you look at the perimeter of the slab, the insulation and the vapor barrier are forming the formwork upon which the slab and the thickened slab edge are going to be poured into. Next slide, please. And then you see the house just gets framed on top of your slab as it ordinarily would. Next slide, please. It's framed very conventionally. We use plywood sheathing for kind of a little bit improved drying potential to the exterior. On the exterior of all the plywood sheathing, next slide, please. We applied a continuous air barrier. So this is a kind of sheet material that gets stapled to the wall and then get taped. This happens to be a somewhat fancy European product. Something like Henry Blueskin works very well. Tyvek, if carefully installed and applied, could do the job as well. You're looking for an air impermeable layer. My preference is for air impermeable, i.e. doesn't let any air through, but vapor permeable materials so that moisture can move from inside to out with very little resistance, but air doesn't. That gives you a lot of resilience in that if moisture gets in, it can get out, but the continuous air barrier keeps the air from moving through, and air is what carries the majority of moisture as opposed to diffusion. So all of the seams of this material are taped. Next slide, please. Particular attention is paid to all of the junctions. So the windows are taped into the rest of the air barrier to maintain continuity from window to wall. What's a little bit difficult to see here is that sub-slab vapor barrier turned up underneath, ran underneath your exterior wall sill plate, turned up the outside of your walls and got taped to the above grade wall air barrier. So we maintained good air barrier continuity from the slab to the wall. I like relying on tape much more than like a caulk, because the caulk is ultimately invisible after it's been installed and very difficult to kind of inspect and visually verify. Whereas tape, it's a lot easier to see and identify any flaws in that application and fix them. Next slide, please. So you can see, Dave, who was the site super project manager on this job, did a great job with the actual execution of this air barrier material. In the foreground, you see something that hasn't been taped yet, but if you look around the corners of the window rough opening, that's about as tight and well executed as it could be. What I like to impress upon, construction personnel is that, I see the craftsmanship of the air barrier and the insulation as analogous to the craftsmanship behind the finished carpentry. To me, it's an equivalent representation of a contractor's skill to show how much care and attention they can give to these parts of the building that are often kind of neglected or have historically not been valued. On the slide on the right, that tan material is the wood fiberboard. As I mentioned, this is a material from kind of compressed sawdust with, so really low embodied energy, really, from comparing it to like a foam material, which is petroleum derived, much more environmentally friendly, considerably more expensive, comes with an additional lead time. So, it's not necessarily right for every project. You can get equivalent, just focusing on the performance, you can use foil-faced polyiso and get excellent energy and thermal performance, occupant comfort. And so you don't necessarily need to go to this level, but it was one of the kind of, guiding principles behind our design, and, the client was fully bought in. And it's got, really good drying potential to the exterior. So in this wall, we have no inhibition to drying either outward or inward. So that leads to a lot of, kind of overall resilience and really good building durability in the long term. Next slide, please. So this shows the interior before anything's been insulated. Next slide, please. And I mentioned that we use dense packed cellulose. So you see a cottony web that gets stapled to the interior face of the studs. The cellulose is blown in. I like blown in products because you don't end up competing for space between the insulation and anything else in the wall, such as wiring or plumbing or electrical boxes. It automatically kind of like fills the nooks and crannies and, gives you a completely filled cavity, which is one of the things that Mike Browne, as the kind of quality control chief, is going to be looking for. Next slide, please. So this is another slide. We are using an interior air barrier and vapor resistance membrane on the underside of the roof. That cavity also gets filled with dense packed cellulose. This is a bit of a unique roof insofar as it's fully cathedralized, but yet still vented. So the whole structure was filled with dense packed cellulose, which by itself is a code and building science no-no. However, we overstrapped the roof on the outside of the structural sheathing with 2x as a vent cavity, and then put an additional layer of sheathing on top of that with a soffit vent basically on either end of the big gable, which allows this roof to vent and allow us to still use a material like cellulose, not have to rely on something like closed cell spray foam, and not have to add rigid insulation to the exterior of this. I could have talked most of this presentation about the roof assembly. Happy to answer any questions, but for now we'll just move on. Some additional progress photos. Next slide, please. We applied a rain screen over the outside of the rigid insulation, so you've got vertical furring strips to create a vent space where air can move behind your cladding. This is really good for letting the cladding dry and promoting, again, low maintenance was a priority, and so this allows us to really extend the life of the siding and prevent anything like mildew growth or anything like that. Next slide, please. Some additional progress photos as the house continues to be clad. This, you'll see on the lower right, a small little air source heat pump. This is what provides heat for the entirety of the house. That's an 18,000 BTU unit, 1.5 tons, and it might even be a little bit oversized. So one of the benefits of investing in the envelope is that you can de-invest in the systems. You need much less heating and cooling than you otherwise would. What I like to say is that together, the envelope and the systems provide the thermal comfort that you're after. And the more responsibility you give to the envelope, a component that doesn't move and doesn't really require maintenance, the less responsibility the systems need to pick up. And so the net result is that the building envelope, the insulation and the windows, do the majority of the heavy lifting of keeping the house warm in winter and cool in summer. And then the heat is just there to kind of top you off. And I looked at the clients, we have an energy monitor in March to use, I think, like 250 kilowatt hours for heating, which is a phenomenally low amount of energy for March. Next slide, please. So this was a ducted system. So rather than use wall-mounted units, we used a single ducted system which serves the whole house on a single zone. This is a hyperheat unit, by the way, so we have no kind of concerns about low temperature cutoff or inability of the system to meet demand if the temperature drops below 0 or even lower. The white box on the right that you see is an energy recovery ventilator. So because we built this house to be as tight as we possibly could, which is good for efficiency and comfort and durability, and not so good for indoor air quality, we put in a system to provide continuous mechanical ventilation to ensure that the air stays healthy. And by doing this mechanically, as opposed to like the old-fashioned way of like letting a house breathe, we can control where the air comes in, filter it, recover heat and moisture, and then provide it to the bedrooms and the living spaces where people actually want to breathe that fresh air. And the exhaust air is extracted from the bathrooms and takes the place of any bathroom exhaust fan. So all of the ventilation is done through this appliance, with the exception of a direct to exterior kitchen exhaust hood. Next slide, please. Domestic hot water is a little bit hard to see. On the picture on the left, you'll see a tank in the background. That's a heat pump water heater. This is an electric domestic hot water system, kind of off the shelf these days. All the major manufacturers make them. They extract heat from the air in the mechanical room and deliver that into the domestic hot water. You know, they do have a cooling effect on the indoor air in the room in which they're installed. There is a compressor built in, so they do make a little bit of noise. So expectations need to be properly set. This is a slab on grade without a basement, where I would typically want to install a system like this. So we just made sure to, you know, put good sound insulation in the walls around the mechanical room. And so far, the client has not expressed any kind of unhappiness about this. Photo on the right, the white box is a solar inverter for a PV system. Go to the next slide, please. And this is about a 7 kilowatt rooftop solar array, which is projected to make the house considerably net positive, to the point where not just the house can be powered by the system, but also an electric vehicle as well. And then I think from there, I just have a few finished photos of the project. This is the front of the house, the interior, and the side of the house. We were talking before how lucky we were to get a nice snowy day for the photo shoot. Next slide, please. You'll see that the roof of the house has not melted any snow. That's always a good sign that the house is working. We're not losing any energy out of the house's hat, and yeah, kind of proof positive that the heat is staying in. And that's all. Thank you for your attention, and I will hand it off to Dave and Laura from one of the two ABAs.
Hello all, I guess we're from ABA number 1, Adams and Beasley Associates. I'm the construction manager. I was on point for delivering this project to our customer. I've been involved with many high design, high efficiency, high performing houses, but this was our first passive house. And there was a learning curve, and there's things that we need to kind of learn about it, but I'm actually surprised at how many things were quite traditional as well. There's not a lot of completely new ground to be broken here. We did a lot of work that was fairly familiar. This is, as we said, a 100% electric house, and you know, I don't think we need to be at this level of performance to be an all electric house. It helps for sure, but for the most part, we built a fairly traditional house with a few aspects that were, designed a little bit more than we typically see. So for the traditional aspects, the next slide, actually, thank you. For the traditional, one more. We have a foundation, which is a slab on grade. And we don't do a lot of that in New England, but this is not new technology. This is all fairly traditional. They've been doing this up in Northwest and Alaska. We call this an Alaskan slab. We've been doing this for many, many years. It's not common around here, but it's not new technology by any means. Essentially, we built a raft out of insulation, and that raft extends out past the perimeter of the wall, so frost really can't penetrate. Frost doesn't go horizontal all that much. It doesn't turn corners all that much. So once it drills down and hits insulation, it kind of stops it right there. So that's how we get our frost protection. We refer to it as coffee cups, that EPS, that polystyrene. This was a little bit higher density. We had some supply chain issues where this is a little bit higher density than what was even specified. But we're also putting, we're putting the foot of the house on this. And the foundation was a little bit of a, the first day or so, we're like, we're really doing this, right? And like, yeah, this is fine. And it turned out to be actually quite simple, quite easy to do. The framing, so the next slide is the framing piece, and very traditional, 2x6 walls, a really robust truss roof, a really deep roof, mostly to get us as much insulation as we possibly could. But we had plywood walls, we had pressure treated plates, we had regular studs, and this felt like we're building pretty much anything we've built in the last, many decades. We had, codes are pushing this right now. We don't see very many 2x4 walls anymore for exterior walls. Code mandates for the most part 2x6 from here on out in order to get our insulation values. So this is all very, very familiar to everybody that was involved. The next slide shows some of the insulation. And we've got a mock-up here on the left of, kind of what we're showing for some of the exterior insulation. I've got 2.5 inches of the Gutex wood fiber, and then another 1.5 inches over that, and then an air gap. We had some insulated headers, which are kind of hard to find, but they make life easy. They are pre-made, ready to go, and just cut them to length, and gives us the thermal breaks that we need. We've got blown-in insulation, a dry, dense pack cellulose. We don't want to introduce any more water or moisture into the walls than we have to, so we go dry pack. And that all is, again, pretty typical. A lot of people are using spray foam. We probably could have. This is a choice here based on the design parameters that this was serving our needs very well. The connection to the outside, you'll see that, and Jordan alluded to it and showed some examples of it, that wood fiber on the outside has a direct connection to the styrofoam insulation, the polystyrene insulation at the foundation. That raft of insulation that we built on comes up and connects directly to this wood fiber all the way up, and then it connects into the roof plane as well. So I've got one continuous envelope of insulation all the way around this whole entire building. Next slide's is for HVAC. Again, so now we're starting to get into some of the different parts, but if you break it down, we've got a ducted HVAC system that provides heat and cooling to the house. It's a single zone, primarily because the house is so small. The design of the small, simple home allowed us to do a lot of things that were just very simple. So we've got a ducted system that provides comfort for the whole house. We've also got a separate system for the makeup air, for the not the makeup, but the ERV, the fresh air intake. So they can be combined. More complex systems sometimes combine them, They don't have to be, and it was very simple for us to have 2 independent systems. So I've got a system at the bottom right corner that is my HVAC, and the white box kind of in the middle is my fresh air. And they don't share ducts. They are separate pieces. And they run to my living space, they run to my bedrooms, and they run to my bathrooms. And then I've got an in and out on the front of the building, and that's it. Again, very simple, very, very straightforward. It's easy to understand. The equipment is a little bit fussier. The equipment is a little bit more, a little bit more efficient. But it's doing the same thing as what we've been doing with forced air systems for a long time. The next slide is showing a plan that I found to be very important. So this is where the performance piece kind of starts to separate from what we consider to be more of a traditional or conventional building. We don't always build with HVAC plans. In the past, we do some rules of thumb, we do some back and notebook figuring, and we figure out what the size of the system wants to be, and we run ducts to where they need to go. These systems are just big enough to be adequate. You don't need to design more. You don't need to build in more and overpower the system. So when you start getting the line between demands and design closer together, we need to make sure that we're accurate. So these duct plans have lengths of run on them. They're calculated for how many square foot of how many cubic feet of air are moving to each room, and how much air we're pulling out of each room. So, and the balancing is already done for us as well. So balancing, so I don't have one room that's like really overpowered versus another room that's kind of starving for heating or cooling. There's virtually no differential in temperature or humidity in this house as you walk from end to end. Whether you're in a flat ceiling bedroom or you're out in a cathedral area, the kitchen, the room works, the house works pretty much the same way. And that's all part of this plan. This plan has already been thought of, the engineering's gone into it, the balancing's part of this, and all I have to do is follow it. I'm simplifying that a little bit, but really all I have to do is follow this, and we followed it very, very closely. And I think our numbers worked out. Our balancing report was done by third party, and the balancing report was spot on. So making sure that as we go through these new efficient homes and these tighter and tighter homes, the engineering that goes up front has to be on there, and you have to follow it. And if you do, the execution of it is quite straightforward and quite simple. Next slide is more pictures of the attic. Again, we call this the attic. It's a pretty clean space. It's conditioned space. It's inside the envelope. There's no real homeowner access to this area as far as like they're not coming up here and storing Christmas trees, and they're not storing all their belongings, although they really could. But we didn't plan it that way, and the owner didn't really expect to use it in that way. So it's a nice clean attic from my point of view, but there's not a lot of room to walk around, and we've been able to go from point A to point B. We keep our runs nice and short and efficient, and it's there to service equipment, and that's really all it's there for. And part of the design was giving us the space to house all of this equipment. Slab on grade, there's no basement, so it's all got to be from above. And on the right picture, you'll see it's kind of hard to see, there's a little white box. There's a remote blower fan there for my kitchen hood. So my kitchen hood is up in here with a remote motor. My HVAC is up here, and my fresh air intake is all up here. And there's plumbing as well. Plumbing is very simple. Probably the most traditional part of this project. We had 2 bathrooms in the kitchen and a couple outside hose bibs, and that's it. There's not a lot going on. And other than trying to keep pipe runs short and trying to keep the minimal amount of hot water distributed out to the house, that's just kind of sitting in pipes getting cold when it's not in use. The plumbing is extremely traditional on this piece, on this house. Next slide should be electrical. And electrical is, again, very traditional. There's no new groundbreaking pieces here. We have, the house is remote from the street, almost 450, almost 500 feet from the street. So we had an underground service line all the way up to the house, but we have a 200 amp service, a single panel, no sub panels because of the size of the house, but all LED lighting, all very traditional, standard, familiar appliances, a well that's run by obviously electrical, and electric hot water. And the solar on the roof has a battery system. So they've got a battery that takes the place of a generator. So we don't even need to worry about a generator that burns fuel or burns any kind of other gases that way. The solar system powers the battery, and the battery is, as long as the sun's burning, the battery is going to be able to keep up. So if we lose power from the street, the battery is able to go, I think it's calculated probably a day and a half without any kind of input from the solar. So even if it's dark of night and it's covered by snow, we got at least a day and a half of battery backup to run this house for until we can get the solar panels charging again. All very straightforward. So the things that are less traditional. So if we keep going on the slideshow, the less traditional pieces are what sets us apart. Air barriers. The air barriers are the make or break of a design of this house. So 100 years ago, no one even thought or cared or understood any of these concepts, and the houses never rotted. Well, they leaked and they had energy transfer, and the hot went in, the hot went out, the air went in, the air went out, and all of that dried the houses out. The tighter we make them, the more we have to manage the water situation. So we have to control our water, we have to control the air, and otherwise we're going to create issues that just traps that water, traps it in the house, and starts to rot things away. So dealing with the air barriers and the moisture barriers and the vapor barriers and getting those details right are the backbone of a building like this. Tighter allows us to use less energy and allows us to use smaller equipment, which is set for the electric field. I mean, we can do everything we want to do in this house on electricity very simply because it's tight and it's efficient and it's well insulated. Getting the right materials in the right order and the right orientation takes some time to learn. There's a piece of that we have to kind of understand and make sure that we don't have any unintended consequences. It's not hard. There's no massive, we don't need a set of tools. We don't need power tools. We don't need, any kind of specialized equipment other than just paying attention and understanding what material you're putting and how you're fastening it to the other materials. The continuous connection between the floor, between the roof, between the windows, the doors, is really the biggest thing we have to learn. The next slide is the equipment, and kind of expanding on that a little bit more. Some more pictures of some of the process, mock-ups of the windows, mock-ups of how we're going to tie those windows in and how the insulation fits around the windows. Mock-ups we found to be a big part of our process to make sure that we got it right, we had it to refer to, and that we got approvals, that make sure that everybody else that's paying attention on this project we're all on the same page and all the same agreement. The equipment selections are important for making sure that we're using as efficient equipment as we possibly can. So the more efficient it is, the less energy we're using, and the more efficient equipment is usually a little bit more fussy as far as trying to get things balanced, trying to get things installed in a proper way. There's a little bit more control that the equipment likes to see. So making sure that we've got the right thermostats, the right understanding of how we're going to use those pieces of equipment has a lot to do with it. So lessons learned. what did we learn on this project? We learned lots. We learned that these houses require lots of tape. Everything is connected with tape. Barriers have their own specific tape that they want to be used with. Some tapes are for joining disc-like materials. Some tapes are used for the inside. Some tapes are used for the outside. Every time that I thought we would place it, we placed an order for tape. About 5 days later, someone would come, yep, we're out of tape. We need more tape. So don't underestimate that portion of it. I think the tape is easy. Jordan referred to it. It's a great visual indicator of whether or not something's done well or something done at all. It's easy to verify very quickly from the ground whether or not something's been addressed. We make lots of mock-ups for how the windows fit into the openings, how they're attached, and how the barriers are tied into them. We would mock something up based on our understanding. The architectural team would come out and yay or nay and make corrections. And during the process, we would say, boy, this was a really tricky detail. What if we did it this way? And it allowed us to actually have real meaningful conversations about how something gets done. And there's obviously more than one way to do something. So the mock-ups are there to kind of help teach and refer to make sure that we're getting these details right. We also use them to educate the inspectors. So the inspectors in town of Acton were excellent. They were behind us 100%, and they were familiar with what we were doing, but at the same time, we showed them details that they weren't familiar with, and that's going to be a natural part of this process as well. So they're going to make sure that we have something that those conversations can be had with. The biggest other piece is buy-in from the subcontractors. So buy-in from all the trade partners is important because this is different. This is important to get it right the first time. It's important. The details really have major impact at the end of the project. And not every trade partner is willing to change their ways or to understand why they're being asked to do something differently than they've done for the last 15 years. So that's a big portion of it. You have to understand why we're doing something and what ramifications we have so we can explain to them why we're doing something differently than they're used to. Supply chain issues are a big deal. A lot of these materials on this project specifically were not at Home Depot. They were not at our local lumber yards. We had to do due diligence early on, getting things ordered, getting things planned out, doing takeoffs early on something that we weren't always familiar with, and trying to get that stuff on site in time so we can keep the project moving. And that proved to be, and we did this during some parts of COVID. So that was another issue as well. We have no bath fans on this project. That was a fun conversation with our inspectors. They didn't understand why we didn't have bath fans, and we had to make sure that they understood that our ERVs and we're pulling fresh air out of our bathrooms and out to the outside and replacing it with new fresh air that's been filtered and conditioned. And we also have controls in place that we could hit a boost button. So that ERV runs all the time, but if we know we're in the bathroom and we know we're creating moisture that we want to pull out, we could kick that up and turn it on and make sure that it's going to have a little bit more boost to it for those times. So there's ways around having no bath fans, and that was one of the things that was a conversation that had to be had. No makeup air for the fans, for the kitchen fan. We did purposely a small, less than 400 CFM exhaust fan, so code doesn't mandate having an exhaust for a makeup air for that exhaust hood. But we couldn't open doors. When we turned that fan on, it created such negative pressure in that house being so tight that we couldn't actually open the door. So we have a passive makeup air system where the fan turns on and there's a passive baffle that opens and allows makeup air as needed to kind of equalize the pressure. Makeup air is important for bigger CFM fans, and we thought we didn't have to worry about it for small ones, but The house is so tight that that fan could instantly lock all the doors, right? Couldn't open doors. And even though you're pulling them in, but they would jam up against the locks and the throw bolts would lock against the jam to the point where you couldn't turn the handle. It was amazing how tight that a small CFM fan could do. Blower doors and infrared cameras. If you're not familiar with those are tools that the third-party inspectors, Michael specifically, will come out and measure the results of your work. So we can test the air filtration. We can find air leakage. We can find leaks in the envelope that we don't want. And it's done by the blower doors. We actually pressurize and depressurize the house and measure it. The infrared cameras can kind of allow us to see that temperature differential. So these are all parts of the early envelope, and it's part of the process that we do before we close walls in. And you have to get it right at that point, because if you don't get it right then, and you put cladding on, you put insulation on, you put siding on, and you get all the pretty parts of the house done, you can't get at these points to fix them again. You've really only got one easy point to make corrections and fix problems and leakage. And that's very early on, right? You know, before rough inspections or during rough inspections, essentially all your mechanicals are done, penetrations to the building are done, and that's your one shot at it. Get it right the first time. You will not want to tear open finished walls and finished siding to fix a problem, because at the end of the project you don't make your benchmark, you don't make your line. The air systems, the HVAC, does not run very often in this home. So we needed dehumidification and dehumidification. We needed to kind of help that system. Usually in a conventional home, we run these systems and they run so much that it just kind of acts as a moisture control. And the systems don't run enough to do that. And so we ended up having a separate dehumidifier added to this project to kind of help with that setup. And I think that's about it for the lessons learned. The business side of things this is a learning curve. There are pieces here that we didn't understand and we didn't know early on, as far as how much time it takes to tape all these windows, and how much time it takes to connect all these barriers, and how much time it takes to wait for barriers to be delivered. So pricing wise, it's something that it's hard to factor in, but we have to factor in the time it's going to take to learn how to do some of these new, these new systems. You're also selling to a niche customer right now, anyways. There's not a heavy demand. Not all of our customers are coming to us looking for this yet. I'm sure ZED and Jordan's customer base looks a lot differently than ours right now. They're coming to them looking for that. But it's not a common, it's not a full-blown common customer yet. So right, you're selling to a niche.
Yeah. So what we're trying to do, Dave, can you just mute yourself while I'm speaking? Thank you. One of the things that we're trying to do is learn from what we're doing here on this house that's taking it to really a wonderful high degree of with the passive house certification. And we're trying to figure out how we can fold that back into sort of our more conventional building. And what I appreciate about this panel is that we're talking about how to bring that to a larger audience. And there are definitely things that we learned on this process along this way that allows us to sell it to the more conventional building customer. And then in terms of the cost, I'm just going to speak again to that. What Dave is getting at is this house, because of its design requirements, was definitely more expensive than a house of a traditional build of this size and whatnot. But what really set it apart, as Dave said, the non-traditional aspects is what made the sort of elevated the costs, in terms of the fact that like we had to go around the exterior of the house multiple times, whereas one like in a traditional build, you go around twice. You do your building wrap and then you do your siding. Here we had the building wrap and then the windows took great care because of all the air infiltration, so that when you're going to the sort of second level of this certification and getting that continuous air barrier on a house, that's what's going to really push the costs higher. And any of the sort of the specialized materials like that fibrous insulation on the outside, yeah, as Jordan pointed out, it was more expensive. That was a choice that the design and the design team and the client chose, so we followed that path. I think that there are ways to do this that are more cost effective, that would be a better entry point for a more mass audience. But it is going to be it's going to be more expensive than a conventional build, depending on your choices will drive that. But I think that codes and I think the mandate to reduce emissions is going to push us all in this direction at some point. So getting ahead of that now feels like an important step for us, and from the perspective of Adams and Beasley. And I think it also is just sort of changing the paradigm. Our consumers are going to, their mindsets will shift once they're forced to do it. So to be prepared and be, it seems important to us to be there with them when we do that. And I think that's our presentation. Dave, do you have anything else to add?
No, I think that's all we have. I think we'll turn it over to Mike next.
Thank you. So my name is Mike Browne, and I did the verification of the project. And that slide looks chopped off at the bottom. Is that zoomed out or? Oh,
yeah. One sec here. I think we're.
Yeah. And you want to go back to the beginning? Back one, maybe? Huh. That's weird.
Hang on 1 second, Mike.
No worries. I'll just keep talking though. So yeah, I am a HERS rater. Our company is Advanced Building Analysis. This is the crew you're looking at right there, our whole company. And we evaluate designs, and we evaluate insulation and air sealing during construction, and we evaluate the completed project. And along the way, we're giving you feedback. And in this case, it was really wonderful to work with Jordan and Dave and Laura. The feedback needed was kind of minimal. We were mostly telling them they were doing an amazing job. But we love to be involved from start to finish and to be able to give feedback at every step of the way. We deal with so many different builders all the time that we feel we're cross-pollinating good ideas all of the time. So as we visit job site after job site after job site, we see lots of different ways of doing things, lots of ways of screwing things up, that's for sure. And we want to help people avoid the pitfalls and get things right the first time. So rely upon your HERS rater for that. They do see a lot, and they see the problems. We're all put in a position of trying to troubleshoot a lot. We get paid to be verifiers basically, but we also end up being troubleshooters, and it's an important part of what we do. That looks fine, Keegan, if that's fine. Yeah, good. Okay, so this, if you want to know more about HERS rating, previous slide. There's a lot from ResNet on the previous slide there. You can go look that up at the ResNet website. There's a lot of information about the whole process. I think a lot of people in Massachusetts are very familiar with the whole HERS rating process right now. What we're talking about is extending that to this group, extending it to get more incentives, and using some other programs to add value and add quality control, and even more than that, to help you with the design. So folks like Jordan can come in and design a project from start to finish, understanding a lot of the core principles and pitfalls that come with the changing landscape here. But for the rest of us who don't have Jordan on our team, we do have these checklists that come from Energy Star and Passive House and LEED and the DOE Zero Energy Ready Homes program and Indoor Air Plus. All these programs are much more than just a checklist. They're a way of guiding you to higher performance when you pay attention to every element on those lists. Next slide. So you'll know it says the blower door guys, and yes, we do a lot of blower door testing. We're used to not only getting the number for you, but then trying to improve it every step of the way. Where every job we go to, we're trying to point out where people can do better. Next slide. This is a building air tightness test report for this project. Look at the CFM airflow. It's remarkable. It's around 200 CFM. These guys said they had a 450 CFM kitchen exhaust hood. So in other words, they were pulling more than twice the air out of the building than our blower door needed to bring it to negative 50 pascals. Negative 50 pascals is like a 25-mile-an-hour wind blowing on the building, or a little bit more. So when they turn on that kitchen exhaust hood, it's like a 50-mile-an-hour, maybe 60-mile-an-hour wind blowing from every direction. That's the amount of pressure that they were putting that building under with just that kitchen hood. Pretty remarkable. Also look at this design and, I'm sorry, look at this page and you'll see the accuracy of our tests. We work hard to be very precise in these measurements, and they tell us a lot of information when we test at negative pressure and positive pressure, and even test at different pressures, which helps us determine the characteristics of leakage in the building, help us figure out how we can best help each particular project do better. Next slide. We look around during blower door tests. We use thermal cameras. Thermal camera is a great way to help illustrate leaks, but also just to find the leaks in the first place. We can quickly scan large areas to show exactly where leaks are coming from. In this case, you can see the dark areas in the corners of this room. This is not the same project. We didn't have a lot to look at in this project. They did such a great job. There wasn't a lot of thermal imagery needed. Here is a picture from their project where I'm getting really nitpicky and looking for the tiniest little leak at a corner with a window here. And again, there are some slightly darker areas, but the really phenomenal job here. Next slide. Heating systems. We are, of course, in the middle of a great push for electrification, and it's really important to design cold temperature heat pumps well. And this is not the standard of the industry. This is a very much a changing standard. So we will try to help you make sure you get a good selection of equipment in the first place, a good layout of the distribution, good controls of it all, and then we're going to also test duct leakage to make sure it works in the end. There's lots of data behind this equipment. Next slide. This is just a little taste of it. It gives us heating performance at 47 degrees, 17 degrees, 5 degrees, even negative 13. And there's a range of performance from minimum outputs to maximum outputs. This particular type of single split system with one outdoor compressor and one indoor air handler, it has an amazing ability to modulate by about a factor of 20 from its maximum output to its lowest output. And it makes it a very effective piece of equipment and really remarkable what they can do at low temperatures now. But we want to help you choose the right equipment to make sure you will meet your low temperature loads and get all of this distributed and balanced well. Next. We used a completely separate ventilation system, like Dave pointed out, for ventilation. This is just the easy way to do it. Trying to combine ventilation with heating and cooling ductwork, although it may save a little bit in materials, is full of pitfalls. There's lots of ways to screw it up. If you want to have fewer screw-ups, completely separate your ventilation from your heating and cooling ductwork. And there's a lot of detail in choosing the right equipment here and designing it correctly to meet the flows needed in different areas and the total flow needed for a home. Next. Here we are measuring the flows in the end. This is a powered flow hood, very carefully measures very low flows that we need in all the different spaces of the building. This type of flow hood is not what a typical balancing company has. Typical balancing companies are commercial companies working on very big systems. This is small. You can see that little thing in my hands there. It measures down to just a handful of CFM very, very accurately. Most of that commercial equipment isn't very accurate below 100 CFM. So be careful who balances your system. Next slide. Oh, this is chopped off at the bottom. This is the annual energy cost. And across the bottom, it tells us the different areas. Reading from left to right, it's heating, cooling, hot water, lights and appliances, and then I forgot what the last one is.
Service charges. Are you're not seeing the full table?
No, we don't see the bottom of the table. Yeah.
Oh, weird. Okay.
Yeah, but I want to point out that we've absolutely minimized the first three here. That's heating, cooling, and hot water. And then the next big section is lights and appliances. That's what remains that in our modeling, we're not allowed to reduce dramatically, right? We have to assume that people will use their lights and they'll use a lot of appliances and TVs and stuff. So after you've eliminated heating, cooling, and hot water as major loads, you're left with that big sector. It's really remarkable that these folks dropped this as much as they did. Next slide. This is a breakout of more of the detailed costs. And you can see here by appliance what you can expect to pay for different types of appliances. You can see the biggest one left in this home, it's the TV. Next. All right, heating and cooling costs. We can drill down further. This is broken out by component of the building: above grade walls, infiltration and ventilation, slabs and floors, roofs, ducts, windows and doors, foundations, and internal gains. So these are all really minute. The scale over here is dollars per year on the left. And this is a pretty good approach. Nothing is really wildly worse than the rest. They've all been very nicely minimized, and you can see that the internal gains, actually, that's what's given off by people living in the building, make up a good bit of heat as well. The majority of the cooling in the here came from windows and doors, and then windows primarily, and then there's a little bit of internal gain that they need to offset as well. Next. I don't need to go into all the details here. I just want to show you the kinds of things we track, the kinds of information we give you. And we're looking in the big picture here. The columns are a HERS reference home and the rated home. The rated home is the home as built. The reference home is what we would expect a new home built in 2006 to have cost. So you can see how dramatically we've reduced the heating to almost 1/10 of the heating cost of a new home in 2006 that's built to code minimum in 2006. We can go down the list, but I want to keep moving. Next slide. This is what you want to see in the end. This is the certificate you give to your code enforcement, and that just needs to be less than a 55 to meet stretch code in Massachusetts. We're at -15 here, meaning they're positively producing energy and not consuming energy across an entire year. Next slide. This shows an Energy Star home report. Again, Energy Star is part of what we did here. It's part of the passive house requirements, and they blew this away as well. Energy Star shouldn't be too scary. In fact, it's a great list of things that are just good quality control and quality assurance on those mandatory requirements, and look at the performance they needed. They only needed a 65 for this small home to be at the performance required by Energy Star. And without PV, this home came in at 26. So you can really blow away even a program like Energy Star. Next. And that's the sticker. It'll go on the home when it's certified. Next. And we also have a few other certifications to go along with this. The Indoor Air Plus. You know, we talked about what the market's ready for and when they'll come looking for the next thing. A local builder in my own town hadn't worked with me for years, finally had someone come to him who says, I have people in my family with asthma and allergies, and what can you do for me to make sure we'll have great indoor air quality in the new home you're going to build for me? And he didn't know what to say. And so that was the reason he finally came to talk to me. He wanted to be able to have something to offer there. And this is the program you could turn to for the guidance, the specifications, in fact, and a checklist of things to make sure you've done correctly to be able to prove to a client that you've taken care of all sorts of indoor air quality issues. Next. Here's another certification that is wrapped in here with Passive House, the DOE's Zero Energy Ready Home. Of course, this one was Zero Energy, but the DOE Zero Energy Ready Home is one that's just built to be able to be net zero when solar is put on the roof. You don't necessarily have to even put it on the roof. You just have to plan ahead for it. Have a design which can be net zero with the roof you got. Next. There's other values to our whole process. One is that we can help you get a good appraisal. Next. And we help compare the new home that you've built to average homes in Massachusetts, both in terms of energy use and carbon footprint, and show how stellar these homes are. In fact, they're when they're negative in terms of their carbon footprint, they're actually helping reduce the problem of carbon emissions. And when you can do that across the board and include embodied carbon in your calculations, which is possible now, the more homes you build, the more carbon you're taking out of the atmosphere. How amazing would that be? Let's build a lot of those homes. I think that's it for me.
Thanks, Mike. Yeah, that's great, and thank you, Dave and Laura and Jordan. Really, really informative and really a cool project. So we've got some questions here. So I think I'll just go through some of them, and I think I can address them to who the answerer should be. So we've got a question here for Jordan. Do you ever vent the DHW to the exterior with regards to the heat pump water heater?
No. So presumably to get that cold air out.
I believe. Yep. Yeah.
Yeah. I don't. A few things. One, you're cutting another hole in the envelope, which you've spent quite a lot of time and effort and money at getting tight. Two, that fan is moving in theory a few hundred CFM. You saw, Dave and Mike talked about what the kitchen hood, the 400 CFM kitchen hood did to pressure in the house. And third, I just don't think that's an approved installation technique per the heat pump water heater manufacturers. You could, if you had a big basement where part of it was finished and part of it was unfinished, you could vent between the finished area and the unfinished area. But in general, no. I try to just have a mechanical room that's large enough for the heat pump water heater, and not vent it.
Right. We've seen a crawl space be the source of air and the endpoint for the air, a way of changing the air in the crawl space with a ducted air source heat pump. And it's an interesting way to prevent air from stagnating down there.
Dave, I think that's a question for either you or Laura. What specific type of windows were used on this project? Dave, I think you're on mute.
I can take that while Dave is resolving.
Sure, go ahead, Jordan. Yeah.
It's a company called Schuco. So these are a European window, a tilt turn window. So it's a dual function inward opening. So it opens inward like a casement and tilts inward like an awning. It's a 3-position handle. European windows are not a necessity to get to this level of performance. Your typical American Pella, Marvin, Anderson, Lowen manufacturers are all making triple pane windows, which are quite good. You know, part of it was design decision, part of it was familiarity, but it's a vinyl window, it's a UPVC window for a pretty affordable price point, especially when compared to some of the American triple pane options. I would suggest that for this level of performance that's targeted, triple pane is likely going to be a necessity to get there.
Yeah, we were very happy with the Schuco windows. They were, the price point was right. The performance was excellent. And surprisingly enough, the lead time, even though it came from overseas, the lead time was actually reasonable as well.
Yeah, domestic window lead times are really long now anyway. So it's like, you know, yes, you deal with it shipping from Europe, but you know, with new construction, you're going to have long lead times pretty much no matter what you do.
Right. It was I think a 10 to 12 week lead time for the Schucos coming from Poland. I think they come from
Slovakia.
Yeah. Yeah, it started as a 10-week lead time, went to 13, I think.
Another question here, and I'll let you guys figure out who's the best one to answer this. Could the metal roof itself have created the ventilation channel? Meaning, was the second layer of sheathing necessary if that were the case?
Yes, I think so. I don't think you get, so my rule of thumb is, and this is based on kind of guidance from Building Science Corporation, who is kind of like the trusted authority on all things building science related, for me at least, is that for a pitched roof, you want at least 1.5 inches of a vent channel, which means 2x strapping. You know, adequate roof ventilation in this sort of pushing the limits roof is not something that I would have ever wanted to kind of try to nickel and dime. And so, you know, thinking about the building as a generational structure, better to do best practice from the outset than to risk having your roof rot. Because you're really getting no outward drying. You know, additionally, worth noting, because it's a metal roof, we have, is it ice and water, Dave, under the whole roof, or?
Yes, yep.
So you've got an ice and water layer underneath your secondary layer of sheathing as your underlayment, which allows zero drying through it. So even if your metal roof ostensibly had a large enough channel for ventilation, it's not going to function at all because you've got no drying, no moisture movement into that, and your sheathing would rot. Right. Which is, technically speaking, a bad outcome.
Was any consider?
Go ahead.
Was it? Sorry, go ahead, Mike.
Oh, I was just going to say, so the point of that vent gap then is that membrane, the ice and water shield, is always cold. If it weren't there, the snow load would act like all sorts of extra insulation, and that would make that throws off where the condensation point is, and yeah, you end up with a moisture problem. Anyway, go ahead.
Was any consideration given to using something like the ZipR system in this project?
Not really. I mean, typically we're targeting a higher level of insulation on our exterior walls than the thickest layer of ZipR can provide. I think that's, you get R12. We've got a bit more than that with our 4 inches of wood fiber board. Plus we avoided the foam material. With the roof, by code, you need at least R20 in a continuous layer, which obviously the ZipR cannot provide. But really if you actually do the math, if you wanted to do an unvented roof with 18 inches of cellulose, you would need probably 6 or 8 inches of polyiso just to kind of balance out your potential, make your sheathing warm enough to prevent condensation from occurring. So, like I said, the roof could be its own its own presentation by itself. We had a narrow building which allowed us to do a single span roof truss great for just packing it with cellulose and avoiding any added foam. So, you know, the decision was combination, like, what is the geometry of the building? What are the kind of materials that we're aiming to use and not use? And how can we most economically build and insulate this roof? And I would hazard a guess that, you know, the strapping and additional layer of sheathing is less expensive than doing 4 or 6 inches of rigid foam, which would then require an extra layer of sheathing anyway, as your, you know, to provide your nailing surface.
So given that we for the project chose to use the more traditional framing approach, was advanced framing techniques explored or considered as an option?
They were. To some degree, they were. I mean, we've got insulated corners, we've got insulated headers, we've got, you know, we don't have lots and lots of jacks and kings and cripples. You know, some of the framing pieces have been minimized, not to the extreme that I know advanced framing can go to, but there is some thought just to eliminate how many pieces of wood that we have to purchase. I mean, for that reason alone, we try and maximize, you know, how we're framing them. So advanced framing to the, you know, to pure definition, no, but there is certainly some consideration to, you know, how much wood we're putting in those walls.
Yeah, everything is 16 on center, but yeah, I think part of that was driven by the structural engineer.
Great. Laura, you mentioned there were a few instances where conventional materials could have been substituted to have reduced costs in certain areas. Do you have any specific examples of things that come to mind?
Well, I think specifically I was speaking to the what Jordan mentioned, the insulation. That's sort of like a low hanging fruit that you could leverage. But you know, your door and window package also matters. That, you know, and I mean, those are the two things that really jump out to me. We didn't have a very, like, the finishes on this particular project were pretty simple. So that was, you know, that was not for us a factor. But those are the things that I was thinking about. I don't know, Jordan and Dave, if you have any other ideas.
Yeah, I agree that the wood fiber board was probably like the single biggest piece of added cost relative to like what we could have done at like a bare minimum to achieve
Right.
Kind of like a level 2 passive house type stuff. You know, for a small house, in the smaller the house, the kind of bigger the premium you pay. If this were, especially because it's less expensive. You know, I don't love like percent of construction as like a metric for judging like the added cost, because like if you have like a really high-end house with like really fancy finishes, then like the kind of division 7 stuff is a much smaller piece of the total puzzle, and like your percentage increase is kind of artificially lower than it would be if you build smaller, simpler houses, which are inherently more energy efficient and environmentally friendly than really big complex houses.
So not surprisingly, there are quite a few questions about costs and you know, how costs compare to traditional homes, et cetera. Does anyone want to take a stab at kind of just addressing the incremental cost to building to this standard comparatively to a more traditional home?
So I think I'll take a stab at that. I would say that our experience with this home, that it was about 30% more than our typical build. That was and from our experience of also some of our project managers and construction managers who have done similar builds to this, that's their experience. This for me was the first passive home that I've done, so I'm speaking from my experience. So this was a big learning curve for me, but that's sort of where we landed. It's like between 20 and 30.
And are you basing that just on like what you would expect dollars per square foot to be?
Yeah, basically. Mm-hmm. You know, I think that there is, you know, it depends on the size of the house, as you said, Jordan. It really, it'll just get bigger. So
Yeah, no, thanks, Laura. That's good. Are you, let's see, Mike Browne, could you speak a little bit more about the clean air certification that you mentioned?
Sure, that's Indoor Air Plus, and
Yep.
it's from EPA. It's an add-on program that's designed to go together with Energy Star homes. And it looks at everything you can imagine with water management and indoor air quality, starting with foundation and drainage, and including drainage plane and materials that you use on the inside of the home, and the ventilation finally. So through all of that, there's a great document, a specification guidebook for Indoor Air Plus that you could pull from for your own particular project, and a brief one-page checklist to summarize everything that's in there. And I just got to add something. I was wrong about what I said about the roof. It's about melting the snow on the roof. If your snow is very deep on top of a very well insulated roof that's not vented, we're keeping the snow cold with that vent. It's not the roof insulation we want to keep cold. See, do you agree with me, Jordan?
Yeah, so I mean, personally, I don't think it's as a real issue in Massachusetts, like if you're building in the Rockies or in the Pacific Northwest where you could get like feet of snow.
Yeah.
The total depth of snow has got enough insulating value such that it can melt the lowest level of snow against your metal roof, and cause ice damming, even though like built a roof that would otherwise prevent ice damming. I don't really consider that when I'm doing Massachusetts houses, just because you're talking about inches of snow, not feet.
I've run into BSC, Building Science Corporation, saying this before, and they look carefully at what snow they expect and the pitch of the roof and everything before they make that determination.
So we've got a few minutes left for a couple more questions, if you guys can hang on. So just to clarify one thing around kind of that incremental cost question, Laura, I think with the numbers that you mentioned, is it fair to say that that cost above what might be typical, some of that is a result of the specific materials that were chosen and selected, and it would be feasible, depending on what is selected, to have that be that overall percentage be lower?
yeah, so as I'd say, I'm speaking to what our experience, and and so our experience is what we did this passive house, which is taking it to the nth degree, which is what the client wanted. So I'm giving you, I think, probably the outside numbers, but if we're speaking to this this program that we're all gathered here to talk about, there are different levels of entry into that, and I think that, to Mike's point, starting at level 1 is going to give you definitely a lower price point, because you're meeting different requirements. So this client chose to meet lots of different requirements. Mike, please speak to that.
This project was also very challenging for this savings calculation because of its size. A bigger home actually would have an easier time getting to 50%. And you remember the graph I showed with the big yellow bar being lights and appliances? That graph is relatively smaller in much bigger homes. So that part of that we can't reduce is a relatively small part, and it's easier to get bigger savings in bigger homes. So you accomplished.
It's kind of like we had sort of like a concentration effect here, where it actually was probably more expensive to do this percentage-wise more expensive to do this more compressed build. I mean, Jordan, you've done a lot of other much larger homes.
Yeah, so 30% doesn't really jive with my experience when we've done cost analysis. On a per square foot basis, you've got a small house with no basement. So you've got very few square feet, and you've minimized all of the inexpensive square footage that would otherwise be included in it.
That's right.
And on a per square foot basis, now kitchens and baths are a much higher percentage of your square footage because it's a 2-bed, 2-bath, 1,600 square foot slab on grade house.
Right.
This house had, I don't know what you're including in your kind of numerator for that calculation, but this house had a remarkable amount of blasting required.
And it's set way back from the street,
right.
so there would like
so
all of the utilities.
All the site work,
yes, so that's everything, the whole thing.
Which I wouldn't do, which I don't think is.
Yeah, so maybe that was an unfair calculation, but that's from just like high level. That's what this.
So my experience is closer to 10%, and it of course is based on what would you build otherwise. And so there's a wide range of like what a builder's baseline is that you're comparing a passive house or an all electric house to. If your baseline is pure code compliance, yeah, you're probably looking at 10%. If you like to build high performance, perhaps not to this level, you know, the added cost might not be, won't be as high as 10%. And if you're building big houses, so we work, when we work with like very high-end builders, some of them will say there's no cost, no added cost, because they just build to such a high level that adding these things doesn't add additional cost for their own practice. Now, obviously, those are the extremes on the other end for the builders.
So like the biggest cost, I mean, one of the big cost drivers, as I said earlier, is like just the pure labor of the envelope. And it's really the envelope that really sets apart this build from anything else. So that the equipment, it's incremental costs. It's not hugely different, as Dave pointed out. You're dealing with a ducted heat and cooling system like that. We do those all the time. It doesn't necessarily have to be all electric, right? That's not wildly different. It's the envelope that sets it apart. And so, and that's a lot of labor. And so just that's really where our experience, that's for us, what's made it different.
Sure. And I often get the question like, what's my payback for, you know, investing in? And it's probably not great if you're spending 30% extra. It might not even be great if you're spending 10% extra, but you reduce your carbon footprint, you make the house more comfortable, you make the house healthier, you make the house more durable, and tell me when I'm listing things that you don't want incorporated into your buildings.
Right, well, I've been thinking about this, and it's really about sort of like a change in paradigm about understanding what the investment is in the house. And you know, when you go to buy a house, you say, okay, what are my heating and cooling costs? Because that's a huge factor in like, can I afford to live here, right? And so that, for me, is what jogs the paradigm shift, is that buyers are gonna need to start thinking differently about how they spend their money when they get into this market.
Yeah, and we've seen a real shift over the years from people coming to us primarily for energy efficiency to people coming to us for maybe primarily for healthy houses that are also very energy efficient. And so when you say we've got no fuel on site, so nothing is burning, there's no risk of backdrafting anything, there's no risk of anything exploding, we've got a continuous source of fresh air, which is always bringing in clean outside air that's filtered to MERV 13 and delivered right into your bedrooms. That, you know, has a demonstrable positive correlation with health. People start to get really interested, and you know, it's kind of like the, you know, I use like the Whole Foods analogy. Like people love shopping at Whole Foods and buying organic food that's been shipped halfway around the world. You know, they're not so concerned about necessarily the energy impact or like the climate impact, but they want that healthy organic food that's coming in.
The home also ends up being very resilient. If the power does go out, power could go out for a week in this home. And I don't think it would get below 50 degrees in there.
I don't think it's possible for this house to freeze.
We are 1 minute past 4:31 here, so I think we can wrap it up. But I just want to thank you guys again so much for your time today and for joining us. Your expertise and your experiences are so insightful and valuable, and we thank you. And look forward to hearing more projects from y'all.
Yeah. Thanks, everybody.
Thank you.